you have to turn fast and not go in the hole very quickly. Well, even if you're drilling at 100 foot an hour, that's not going in the hole very quickly. That's really slow axial velocity. So it doesn't take much RPM to make almost all of your axial friction completely disappear. And I'll send you guys a spreadsheet that basically works that out, and you can run the little numbers and see the arrows change. But essentially this VR is oriented almost entirely in the same direction as VC. This thing is pointed way over here because I've got very little VA. Now, nothing's for free, unfortunately. There is a fixed, limited amount of friction. Let's just say there's 100 pounds of friction. If 90% of it is acting in the circumferential direction, well, then 10% of it is acting in the axial direction. That's where we do this little calculation here. Friction factor for torque, effective, is just my normal friction factor, times my circumferential velocity divided by my resultant vector. So here I'm dividing my axial by the resultant, here I'm dividing the circumferential by the resultant. And the two kind of balance out to a net sum of friction. If you've got all torque, you're not going to have drag. If you got all drag, you're not going to have torque. That's basically how it works out. Here's an example from the software. This is a long high angle well. We know it from the trajectory, right? Here's our drill string, just a real simple drill pipe in the hole. The red curve is pulling out, the green curve is rotating in one place, and the blue curve is slacking off, trying to run the drill string in the hole. Well, this axis right here is zero tension. That's your no-go line. When the slack off weight, when you're lowering the string in the hole, if I have no more tension at surface, the pipe won't go in the hole. It'll just stand there and look at you and say, ha-ha. So you would have to push on it with lots and lots of force to get it to go in the ground. Or we have to rotate. So we can simulate in the software what would happen if we rotate. So I'm going to change from 0 RPM to 60 RPM. I'm tripping in the hole at 100 foot per minute, and when I turn at 60 RPM, now the blue curve doesn't go below 0. That means the string will be able to go in the hole under its own weight. If I turn it faster, it gets better. Notice that the torque increases though. If I slow down the run speed, then I've got essentially no axial friction. Rotation is one of the most powerful tools that you can have in an extended reach well, whether we're talking about drilling, or tripping, or running casing. It's all about configuring equipment to be able to be rotated. That's why torque is such an issue. This whole conversation started with torque, but I got to make sure that this line doesn't exceed the strength of my equipment, torsionally speaking. I need strong tool joints and a strong top drive to cope with the torque that I create by turning. Does this make sense? Does it seem like it's more like a freshman level class rather than a senior level discussion? The other reason why I have to rotate is hole cleaning. And this is a really misunderstood topic. And I'm going to condense it down to just a couple of slides. So basically in a deviated well, pipes on the low side, dirt's on the low side. Because of that, all the mud channels up the high side. That red area is where the mud's moving fast. The mud is moving exceptionally slowly on the bottom. We like to think of it as a conveyor belt. You have to turn the pipe fast to throw the dirt up onto the belt. If you're not turning fast enough, there's no hole cleaning. So yeah, could coiled tubing drill an extended reach well? It could, but it would have to be a very small hole and the fluid would have to be in turbulent flow. The vast majority of the time, we're not in turbulent flow. When we drill with mud, anything other than water or close to water, we're in laminar flow. And laminar flow looks like this. Slow moving mud here, fast moving mud here, slow moving mud here. So we have to turn to stir up the dirt. Vertical wells don't deal with this problem because the mud's going up and gravity's pulling down. It's easy in vertical wells. We don't have to turn. The slip velocity is all that we're really battling. So if you just throw some viscosifying agents in the mud, you're able to lift the cuttings out of the hole pretty easily. It's not too complicated. In fact, there's some real easy equations. You've probably even done it in 301. Calculating slip velocity, maybe? If not, I'll send you a spreadsheet. I got a spreadsheet for all this stuff. Horizontal well, we turn it on its axis. So now the mud is going along the well path, but gravity pulls the dirt to the low side. And it's just like a bullet projectile problem. Did you guys ever watch much Mythbusters?
Oh, yeah.
Yeah? You remember the Mythbusters one where they're in the big warehouse down in California and they've got a gun that they fired inside in this warehouse, and they've calculated how far they think it'll fly, the bullet will fly before it hits the ground, because they know the gravitational velocity, they know the speed of the bullet, so we can calculate those things. And the adage goes that if you were to drop a bullet and fire a bullet at the same time, if they were at the same height and you dropped one, you fired one, they would both hit the ground at exactly the same moment. Well, they wanted to test it, so they set up this high-speed camera, and they had a servo that was connected to the trigger of the gun. It was like, I don't know, 300 yards away or something like that. They fired the gun, dropped the bullet, and they had, with a high-speed photo, they showed the two things hitting the paper on the ground at exactly the same moment. Physics works. Physics works. Here's the scale of our problem in hole cleaning. High-speed angular velocity, amazing hole cleaning happens at 200 foot per minute. I can walk at 200 foot per minute. So here you've got your happy little dirt particle, and it's flying up the annulus at 200 foot per minute. And it's got to travel 30,000 feet. Dirt is on the low side. That is the thing that nobody wants to admit. Drilling engineers are a bunch of alcoholics, literally and figuratively. You can't help an alcoholic until they admit they have a problem. Drilling engineers, you cannot help them with their hole cleaning problem until they admit that gravity wins. Gravity always wins. Dirt's on the low side within just a few feet. So it's not a matter of, ideal flow rate or ideal gel strength or anything to do with mud properties. It's not about the mud, it's not about the flow rate. It's about constantly combating the dirt and throwing it back up onto the high side of the hole. So this is this slow, continuous process of hopping, skipping, and jumping cuttings up the hole. It's not about suspension. Cuttings are not in suspension. If anybody ever tells you in a horizontal well that the cuttings are in suspension, call bullshit. They are not. It is physically impossible. Gravity always wins. Medium angle wells are a little bit better, but dirt still falls to the low side of the hole. It travels a little bit further up the hole than it would in a horizontal, but it still ends up on the low side. The bad part about medium angle wells is once they fall to the low side, that's not where they stay. You've got this angle of repose thing happening, where if you're at 45 degrees inclination, when you turn the pumps off, the dirt avalanches down on top of you. So good hole cleaning is actually more important in a medium angle well than it is in a horizontal well. Because in a horizontal well, the cuttings aren't going anywhere. When you turn the pumps off, that's where they stay. Whether the pumps have been off for 5 seconds, 5 minutes, or 5 days, the cuttings are no more of a hazard to you. You will not get stuck because of the cuttings in a horizontal well, just by sitting there with the drill pipe. The reason why you get stuck in a horizontal well is because you try to pull the BHA out of a hole that isn't clean. So hole cleaning is most important before you trip. It's not that important while you drill. You can drill a filthy hole. As long as you're going that way and the cuttings are going the other way, you're fine. But when you go to trip, that's when it has to be clean. Medium angle wells, even before you shut the pumps off, you have to make sure the hole is relatively clean, because as you're shut down, the dirt's coming to see you. It might take 5 minutes, it might take an hour, it might take 2 hours, I don't know, but it's coming to see you. We know that for sure. Hard to clean, but you don't have to worry about where the dirt is. A little bit easier to clean, but man, I lose sleep at night drilling medium angle wells. I hate medium angle wells. Or vertical wells, which is, that's for the Aggies. No more niggers drilling vertical wells. I have to change this when I do this talk at A&M. Texas Tech, those dumb Red Raiders, they don't know. So we've got a conveyor belt. Pipes on the low side, mud's on the high side. You got to turn fast, and there's a threshold speed. It's not just the act of turning, it's this thing we call viscous coupling. There's a layer of mud, this film of mud, that's spinning adjacent to the pipe. The faster you turn, the bigger it gets. And if you make it big enough, you're able to activate a lot more energy into the cuttings that are on the low side. What we've observed all over the world drilling extended reach wells is that until you get above about 120 RPM, almost nothing happens. You get some dirt out of the hole, but it's really trivial compared to what you get when you break over the 120 RPM threshold. Something magical happens. Unfortunately, we don't know exactly what it is. We think we know, but we don't really know. Nobody's built, this might be a good grad student project, nobody's built a full-scale flow loop that duplicates this phenomenon. So University of Tulsa, Calgary, BP, Shell, a bunch of companies, MI, have dumped money into flow loops to try to understand rotary speed, flow rate, rheology, relationships. But they've all made flow loops that are like this big. And what I just told you is we're doing stuff that's like this big. And so they haven't scaled things properly. You can't scale gravity, and you can't scale the tool joint to drill pipe ratio. And I think for that reason, what they've come up with is a curve that looks like this. Most hole cleaning software is absolute garbage because it's based on flow loop experiments that were too small. They tell you that rotary speed's not important. This blue curve is what academia would suggest hole cleaning looks like. Landmarks, well plan software. This is what most companies use. That was supported heavily by BP and Shell. They are still of the notion that rotary speed's not that important. Well, I'm here to tell you that when you actually go to the rig and you actually see what happens when you get the rotary speed over 120, it's impossible for that blue curve to be right. The red curve and the blue curve can't coexist in the same universe. Either one of them's right, one of them's wrong. And the nice thing is this red curve is really easy to prove to yourself. Go out on any horizontal well, and you drill for a while at 100 RPM, and then you drill for a while at 130 RPM, and you tell me if there's more stuff that comes over the shakers. It's not like a little trivial difference. It's like, holy cow, where'd all that come from? That's amazing. No wonder we had so much trouble getting out of the hole. There's a couple Norwegians that figured this out back in the 80s, and they even published papers on it, but for some reason we've just ignored them. But yeah, if you get over 120, most extended reach wells are drilled with this drill string rotary speed. Some of the bigger projects will even get up over 180, but most of the time we're over here. Good grad student project, because we don't exactly know what's going on. We do know that in small hole, there's still a step change, but it's not as pronounced as when we're in big hole. So in like 8.5 inch hole, you can get by at 80, 90 RPM. That's fine. But in big hole, 120 is an absolute minimum. People have paid us millions of dollars to tell them to turn the drill string faster. Yeah, I can't figure out where, I don't know, there must be a mud problem. It's always a mud problem, right? You could probably listen. It's always the mud's fault. Right? It's not the mud. If you're not rotating and you're not patient, this process takes a while, then dirt doesn't come out of the hole. We think what's going on, based on our own limited laboratory experiments, is that as you turn faster, the diameter of this film of mud gets larger. At the same time, the pipe starts to walk to one side of the hole, climbs up a little bit because of friction. And we think at 120, the width of that viscous coupling layer exceeds the diameter of the tool joints. And at that point, we start to create turbulence just through rotation. We're not inducing turbulence through just normal flow mechanisms, but through rotation, we're creating turbulence, which puts more energy into the cuttings bed and allows it to get onto the conveyor belt. The reason why we think that's the case is because most drill pipe has a consistent gap between the tube and the tool joint. Most of them are about 5/8 to 3/4 of an inch gap between the tool joint and the tube. Originally, we thought this was vibration. If it was vibration that was always happening at 120, it wouldn't really make sense because the critical harmonic of the drill string depends on the length and it depends on the dimensions, like how big the diameter is of the pipe. It's harder to vibrate 6 5/8 pipe than it is 4-inch pipe. But we see this phenomenon regardless of whether it's 4-inch pipe or 6 5/8 or anything in between. It's not exactly 120, but it's very close to that range of 120. So, I don't know, throw that out there. If you got grad student looking for a project and somebody that's willing to give you $1 million to build a flow loop, you could probably figure this out. We patented the idea, in fact my name's on a patent, of roughening up the drill pipe to try to enhance the viscous coupling layer. So we experimented with different surface coatings to try to decouple or enhance just how much of this is going on, and we definitely found that there is an impact depending on what surface finish you put on the pipe. Just didn't go anywhere, so yeah.
I'm gonna go build a flow loop.
Okay, go do that. We can all be billionaires. All right, so that was just a long-winded explanation of why we need to be able to rotate. To overcome torque, we also go with really strong stuff like bigger top drives, higher strength material, or Alcoa is one of the companies that is really pushing lightweight materials. Aluminum drill pipe, even titanium drill pipe is starting to make its way into oil and gas. ECD, this one is real interesting. The problem here is we've got long wells but not much true vertical depth. And what it boils down to is rho GH. Everybody remember rho GH? You want to figure out hydrostatic pressure? That's just the density, rho, times G, gravitational constant, which is the same on planet Earth everywhere. Or H, which is the true vertical distance or height between the top and the bottom of the column. So pressure equals these things, or another way of thinking of it is density equals these things. Density equals pressure divided by GH. So when we talk about equivalent circulating density, we're trying to take a pressure that we know. We've measured a pressure, and we're going to convert that into essentially what would the density be? If it was static, if it wasn't moving, how dense would the mud need to be to create that pressure? That's all ECD is. It's super confusing to a lot of people, but that's all it is. It's really just those 4 terms. Here's what it looks like in a vertical well.
You're lumping friction in with real density.
I am lumping friction in with hydrostatic pressure in this P term. So that's the problem. It's not really rho anymore. It's like effective rho.
Magic.
Should be rho prime. Yeah, magic rho. Because in this equation, you normally just think of it as static pressure, static density, static pressure. Well, equivalent circulating density is taking that static pressure, adding the friction pressure, and then making this bastardized thing called ECD, which is fake density. That's maybe what we should call it, fake density. What's your fake density today? Or like the Double E's are able to get away with it with their imaginary power and imaginary density. I think we came up with a new term. Vertical well, this is what it would look like. Let's say that you've got static mud weight and static pressure is this blue line. So we've got depth versus pressure. Of course, we've got a frac gradient over here. We've got pore pressure over here. We want to stay between those two lines. When we turn the pumps on, we create friction. So my friction line, or my dynamic line, is this one right here. If I drop below pore pressure, I either take a kick or the hole collapses. If I go above frac gradient, then I create a fracture and I lose returns. So I got to stay in that window. Here's what it looks like on my horizontal well. Now the horizontal well problem is I still have the same length. I create the same amount of friction pressure. The gap between here and here is exactly the same as the gap between here and here. Friction pressure is the same. Hydrostatic is lower, but because my rocks don't get stronger, when I drill vertically, the rocks get stronger and stronger and stronger and stronger. That's what this is trying to tell you, right? Frac gradient goes up as you get deeper. When I drill a horizontal well, I'm drilling through the same rock, but just further and further and further and further and further. So the frac gradient is not increasing, but the friction pressure is increasing. And eventually the friction pressure becomes in excess of the fracture gradient, and at that point I frac the rock through ECD. When I turn the pumps off, the fracture closes because my static pressure, this blue curve, is still below frac. When I turn the pumps on, the fracture opens. When I turn the pumps off, the fracture closes. That's something that people used to call ballooning. Ballooning is a total horseshit term because it creates this image of the borehole diameter growing and shrinking, growing and shrinking. Rock is not that elastic. The rock cannot grow so much that you lose 500 barrels of mud, and then all of a sudden those 500 barrels of mud come back when the diameter shrinks. Rock's not that elastic. However, we create a lot bigger container when we frac the rock and open up this wing that can store a lot of volume of mud, and then when we take the pressure off and the fracture closes, the mud comes back. So breathing, I think, is a better term. I don't use the term ballooning anymore. But that phenomenon is exactly what goes on in a lot of shale plays. Impermeable rocks, where you see a lot of breathing or ballooning. Impermeable rocks, if you were to frac a sand, when the mud gushes out there into the reservoir because it's got porosity and permeability, it absorbs the mud, and you don't get the mud back. Mud's gone bye-bye forever. But in shales, you get it back. Pumps are on, it goes away. Pumps are off, it comes back. Throughout the process of constructing our wellbore, we want to make sure that the static and dynamic pressures always stay between pore pressure and frac gradient. Or really, what I should say, minimum horizontal stress. I don't like this term frac gradient. Pore pressure, collapse pressure is my lower limit. Frac pressure, or really minimum horizontal stress, is my upper limit. Hydrostatic in the middle. When I trip out of the hole, why would the bottom hole pressure go down? Swab effect. Yeah, the act of pulling out creates friction pressure, but it creates friction pressure in the opposite direction as running in. Surge and swab are the same thing, just in opposite directions. So pulling out reduces bottom hole pressure, going in increases bottom hole pressure. Drilling increases bottom hole pressure even more because I've got cuttings and the pumps are on. But running casing and cementing are a couple of the worst things that I do in my well. Why is that? Why do I have higher bottom hole pressure when I run casing than when I'm drilling?
Making the hole smaller.
Annular volume decreases.
Your annulus is smaller. If you're doing it right, your casing is bigger than your drill pipe. You know? 9 times out of 10, your casing is bigger than your drill pipe. So if I drill an 8.5 inch hole with 5 inch pipe, I'm probably going to put 5.5 or 7 inch casing in. With a smaller annulus, there's going to be a lot more friction that develops as that mud moves through that tiny little space. Now, cementing is like the worst thing that you can do because cement is heavy and cement is thick. So I've already got a narrow annulus, and then I'm going to pump this stuff that looks like peanut butter down there. So it's no surprise. We should never be surprised if we drill the well without lost returns, but then we lose returns while we're running casing, or we lose returns while we're pumping the cement job. The problem is if we lose returns during the cement job, we just screwed up the cement job. So I consider it my responsibility as a drilling engineer to make sure that all these things can happen without fracking or without kicking or collapsing. That is the only acceptable situation. That's not, most drilling engineers stop right here, if they even start. Most of them don't even start. But we need to carry it through to the whole delivery of cementing the well. We're trying to stay in this green window, and when we talked about it in the 401 class, we're kind of getting to this geomechanics model where we can calculate the point at which we collapse, the point at which we start having losses. We want to live in the green spot. 5 minutes for questions.
Do any wiper trips only for Clean Reach wells, or mostly rotate and?
You know, wiper trips have kind of gone away the past. They used to be, certainly when I started, every 500 feet, every 1,000 feet, you wanted to pull the string through to make sure that we could trip. And kind of where the industry's gravitated towards is that if you're really watching things carefully while you're drilling, if you have the right parameters, the cuttings bed height won't grow. It reaches an equilibrium height, and then as you drill ahead, the entire wellbore has a fairly uniform bed height. And once you get to TD, you circulate and you rotate from many bottoms up to get the cuttings removed, and then you pull out. The wiper trip concept of drill, stop, drill, stop, drill, stop, doesn't really get you to any safer situation, because when you clean up the wellbore, once you go back to drilling, there's a certain volume of cuttings that have to be redeposited in the wellbore to build up a certain equilibrium bed height before you even get anything out of the hole or see any cuttings with the shakers. There's like this wellbore storage effect. There's a certain volume of cuttings that the wellbore always stores while you're drilling ahead.
Are you seeing many companies measuring their returns or how much dirt they're getting out of the hole?
I mean, more than, say, 5 or 10 years ago, but the equipment is a little bit cumbersome to retrofit on existing rigs. On new build rigs, a lot of people are using them, so the drill ships and the floaters are getting them, but the technology is kind of interesting. They put these scales in the front of all the shakers, and all the cuttings fall onto the scales. And so you weigh the scales, and every 30 seconds or so, the scale has this robotic arm that dumps the dirt into your cuttings processing system. So if you're always keeping track of how the weight of the rock that you're getting out, if you happen to know the density of the rock, then you can back calculate the volume of rock that you got. So you can compare the volume that you drilled to the volume that you got out to kind of get a feel for how much you're leaving down there. And so some places, Norway, it's pretty big, West Africa, it's pretty big, but like U.S. land, man, I haven't seen one in U.S. land. So. I think Conoco did an experiment with them a few years ago on one of the rigs. I can't remember what it was.
Exxon was doing it a year ago.
Exxon was doing it? Yeah. There's simple ways to do it too. Like if you're having to ship all your cuttings off location, even if you just put them in the back of a dump truck, just count how many dump trucks leave location. You get a relative indicator of how much rock you're getting out.
Can you do this offshore? An offshore rig basically, and dump all the cuttings in the sea maybe?
So if we use water-based mud in a lot of places, not everywhere, some places are more stringent, but most places you can dump your cuttings offshore. So we don't get any record of what we're getting out. But the vast majority of offshore, and certainly deep water wells, use oil-based or synthetic mud. And even with synthetic mud, like in the Gulf of Mexico, we can discharge it as long as we pass certain environmental criteria. But through the process of moving the cuttings, drying the cuttings, getting all the oil off of them, and then shooting them overboard, we can get an accounting of how much rock we got. Water-based mud is really hard anyway because it starts to dissolve the rock, and we get a lot of swelling and expansion, and it's a crapshoot with water-based.
The conveyor belt idea, really neat graphic, very good picture. You talked a lot about the effect of rotational velocity. How much effect is there on mud viscosity? How much does that matter?
It definitely matters.
Do you hit a threshold somewhere? What's going on?
There's like an ideal range. And so what we tend to key in on is the low shear rate viscosity, the 6 and the 3 RPM reading on a fan viscometer. And what we generally say is when that number is somewhere around 0.8 to 1.2 times the hole size. It seems like with bigger hole, you need it a little bit thicker, smaller hole can be a bit thinner. But when it's somewhere between 0.8 and 1.2 times the hole size, then that viscous coupling works really well. When it starts to get thinner than that or thicker than that, then the viscous coupling doesn't work as well. Well, I shouldn't say the viscous coupling. The viscous coupling definitely gets stronger the thicker your mud is. But the problem is that high velocity zone on the high side of the hole, when your mud's too thick, that thing starts to shrink.
Oh.
And it gets too far away from the drill pipe, and so you can't get the dirt up on the belt. You have to thin it out, but you don't want to thin it out too much. You can get it really thin, it's great because it's huge, but then you're not able to transfer the energy from the drill pipe to that viscous coupling layer to grab the dirt and throw it to the high side.
Basically, you have two regimes, two different flow regimes, and they have to be in balance.
You gotta balance them out.
Okay, nice.
Unless you're so fortunate as you're able to drill with water. So water is a great drilling fluid because you, in turbulence, almost the minute that you touch the rheostat for the pumps, because at very low flow rate, water's in turbulent flow, and that turbulent action stirs up a lot of material. But in most places, you need higher density in order to combat the pressures of the rock, higher than 8.33 pounds per gallon. And so in order to get the density up, we have to add stuff like barite, and the barite won't stay in suspension in water, so we have to put viscosifiers in there, and the viscosifiers break us into laminar flow. So water or brine, if we can drill with clear fluids, turbulent flow works all day long. But most of the time we're drilling with mud, and mud, you need some mechanical agitation.
So I saw that at 120, you think that that's where that viscous coupling is getting the size of the tool jump. There's another jump at 180. What's your thought?
I don't know. It might be that there's another turbulent regime that we hit, or maybe the viscous coupling layer starts to hit the edges of the hole. I don't know. We really don't know. That would be an interesting thing to figure out, though.
So that leads me to my next question. So you thought that it got to be about the size of the tool joint. Have you tried internal offset drill pipe? Has anybody done any? I know we hardly ever use it, but has anybody looked at it?
That was like on our chain of things that we were going to experiment with right before Summers ago. So we did a lot of this experimentation work, like in 05 to 07, and then Summers brought us in 08. And yeah, we were like, hey, okay, let's try these different finishes. Let's try smaller tool joints, bigger tool joints. Let's try no tool joints. Just see what happens. And when they bought us, we don't make drill pipe. We don't care about this. So yeah, I don't know. It would be an easy thing to set up an experiment for. I could show you a couple of the videos that are kind of cool. It all started with something incredibly simple. We have this engineer. He's from Ecuador. His name's Luis, and he is always kind of the guinea pig. Kind of mean to him actually, but we had him get a bucket of paint and a piece of PVC pipe. This is our multi-million-dollar research facility. So, bucket of paint, piece of PVC pipe, and then a drill. And he's just playing around with spinning this thing. Right now it's pretty slow, but you can see the viscous coupling layer. And paint has a similar rheology to mud, a little bit thicker. But in a minute he cranks it up fast and he moves this tube over to the side of the bucket, and you'll start to see some turbulence develop at the edge of the pipe. You say, well, okay, there must be something going on there. That's probably not what it looks like downhole, but it's at least the start of something that would suggest that we've got some different behavior happening when we turn fast enough. So then we built a bigger flow loop and we experimented with water and different surface finishes. And the reason why this was, I kind of find it funny, is on his early videos, he's got his dad helping him, and his dad doesn't speak English, so they're speaking Spanish back and forth, and he's got the drill spinning real fast, and he's moving it up and down in the paint can, and so he's got it like full bore on that drill. And he pops the thing out of the paint accidentally. He's in the garage, and it just pink paint everywhere. And so you get all this cursing in Spanish. And it's hilarious. Ay, Dios mío! So we took that to our animator, and he made this. Right? So when you're drilling along and you have high rotary speed, your dirt is hopping and skipping and jumping on the bed above the BHA. You don't have a hole cleaning problem around the BHA itself, or even some distance above the BHA, a matter of distance before the dirt falls out. But when your rotary speed drops too slow, then this bed height just starts building and building and building and building because you're not moving that upper layer. There's this thing called saltation flow that happens in the lateral. And so there's there's a static lower layer and then an upper moving layer. But the upper moving layer requires some rotation to encourage it to get it to move.
So bridging the gap between the science and what really happens on the rigs, have you found any magical ways of inspiring drillers to drink the Kool-Aid? I mean, I've seen lots of rigs where you gotta be above 120, you gotta be above 120 to get back to the office, and you look at the monitor and they're rotating at 40 or 60.
So directional drillers are the spawn of Satan. They're the ones that will inhibit rotary speed more than anything. It started with steerable motors. So most of the time when you have a steerable motor in the hole and a big bend setting. So big bend settings on motors is the sign of a DD with bad habits, right? He probably has 3 ex-wives and affinity for cocaine if he has a 212 motor in the hole. Because that's just poor directional drilling. The only reason why that's in the hole is to minimize how much time he has to spend sliding. And so he's rotary drilling more often than he slide drilling, which is fine if that's all you're interested in. But one of the major disadvantages of that is that the bigger the bend setting, the lower that you're allowed to rotate for fear of fatigue damaging the motor. With big bend setting, there's a lot of bending stress in the motor, and so with higher revolutions, you fail it faster. So what tends to happen with a motor in the hole is the directional drillers say, hey, you can't rotate this thing more than 80 RPM because you'll break my motor, and you don't want to break my motor because, you know, if the motor breaks, the rig will fall over and, you know, we'll probably kill everybody on location. And there's always some horror story for why you can't rotate fast. In reality, I mean, yeah, maybe you'll break the motor, but if you do, it's not going to kill anybody. So the directional driller will tell you all sorts of horror stories why you can't turn fast. Even when we have a rotary steerable tool in the hole, they generally don't want you to turn fast because it's more wear and tear on their equipment. When you're working for ConocoPhillips, you're paying to rent that tool. You don't have to pay for the wear and tear. That's kind of something that they assume. So they make more money off of you if they're able to extend the life of that tool as long as possible. So that what would be ideal for them is if you would pay them to drill the hole, only they didn't have to turn their tools. If they didn't have to pump through them and they didn't have to turn them, that would be perfect for the direction. Maximum profit for them. But as soon as you want to pump through them and turn them, then unfortunately that wears out their stuff. So it does take education. So K&M, one of our main businesses is training. So companies like ConocoPhillips will hire us to get directional drillers in the room, the tool pusher, and kind of remove people's misconceptions. There's been years of misconceptions about the way things work downstairs, and when you show them a few videos and some of the science, and they're like, okay, you know, that makes sense. You know, I guess we're going to have to just suck it up and give it the program because it's not fun for anybody to get stuck or to lose wells, and so. You know,